Hello friends, welcome back to the Hard Surface Modeling video series. In this video, we will be learning about the importance of edge loops and edge flow in the subdivision surface workflow, including where and when to place edge loops and how to control the subdivision algorithm using them. This section will be more theory-oriented than the last, but once we understand these ideas, our ability to create will rapidly increase. Let's get straight into it with the first example. Over here I have a simple cuboid with a cylindrical cut straight through it. You should be able to model this with the knowledge you gained from the previous video, but let's quickly model this together for the purpose of this example. Spawn a plane, subdivide it twice, and inset the faces. Now we can right-click, go to Loop Tools, and choose Circle. Delete these faces and extrude the plane down, and there we have the desired shape. You may need to recalculate the normals, so press Shift-N. Now let's learn about edge loops. Although this mesh has an all-quad topology, if we add a subdivision surface modifier with one level, you can see that both the internal circular edges and the outer edges have collapsed and are no longer sharp. This happens because for every level of the subdivision modifier, each face is split into 4, or you could say each edge is split in 2, and is then smoothed out using the Catmull-Clark algorithm. Understanding the Catmull-Clark algorithm is essential to developing a deeper understanding of 3D modeling. I will explain it briefly, but feel free to read up about it online. Fundamentally, the algorithm creates a bunch of new vertex points, placing them at the midpoints of the edges and faces. It then connects the new vertex points with the original mesh. This generates two important results, which we will be studying in this video. 1. Adding geometry to our mesh. 2. Applying a smoothing effect and removing sharpness. Let's duplicate our object, apply the subdivision modifier, and move it aside. If you go into edit mode, you can see that in the case of the subdivided object, the original edges of our cylindrical cut have been smoothed using the Catmull-Clark algorithm, which determined the midpoints between the outer edges and inner edges of this shape, positioned a new loop there, and the original inner loop was smoothed out slightly with the same method. However, because our inner loop was circular and our outer loop was rectangular, the smoothing effect has created a loop that isn't either, it is not circular or rectangular, rather a perfect mix of the two. Therefore, this has disrupted the shape of our cut. This also explains why the loop added around the side of the model is straight, as the original loops on either side of it were identical, therefore the subdivided result will resemble the same shape. Let me show you a visual representation of what is happening to help understand this. Over here we have the same shape we created before, drawn out in orange. Let's imagine we applied a one-level subdivision to this shape. A new vertex would be placed at the midpoint of each edge, and a loop would be threaded through all these edges. Because one of the original loops was circular, and the other was rectangular, the edges are not all equal in length, therefore the location of the midpoints vary, and the resulting loop is perfectly skewed to fit in between the original loops. Now that we understand what is going on behind the scene when we subdivide an object, we can figure out how to fix any issues. If we want our inner edges to stay circular when subdivided, we have to make sure the neighboring edges on either side of the loop are also circular. Remember, the Catmull-Clark algorithm creates new edges by calculating the midpoints between existing edges. If the existing edges are circular and rectangular, the resulting edge will be a mix of the two. However, if both edges are circular, the resulting loop will be perfectly circular. Finally, this is where edge loops come in. Let's go to our unsubdivided object and select the inner circular edges. Bevel them with Ctrl-B, use two segments to support the original edges on both sides, and change the shape to 1 so that the original edges don't smooth at all. Now when we look at the subdivided model, we can see the inner region has stayed perfectly cylindrical, and is much sharper than before. Let's do the same for the outer edges, bevel with two segments and a shape of 1. This object now keeps most of its original form whilst being subdivided. The shading is now perfect, as each loop is supported, and the shape stays sharp, as the supporting edge loops are very close to the main edge loops, not giving the Catmull-Clark algorithm much room to smooth the mesh. Luckily, Blender has a system to make this easier for us. Instead of beveling every edge, we can use creases, which are the topic of the next section, However, it is important that our foundation of understanding is rock solid, so that we are confident in our understanding when moving on to more difficult and complex topics. Let's move on to the next example, which will highlight another important topic. Once again, spawn in a plane and cut a 16-edged hole in it using loop tools. This time, instead of deleting the faces, extrude them downwards and then delete them, then refill the area with a grid fill. Take the outer edges and extrude them down, and perform a grid fill on them too. Once again, we have an all-quad mesh, but if there's one thing we've learnt, there's more to making a model than having all quads, and having all quads doesn't necessarily mean the subdivision shading or the sharpness of the model will be perfect. For that we need strategically placed loops and supporting edges. So let's analyze why this model doesn't subdivide well. The top loops can be fixed with a simple bevel as we have done before. Remember to use 2 segments and a shape of 1. However, both the bottom outer loop and inner cylindrical loops are more complex. A glaring red flag when working with subdivision models is that when you try to select a loop using Alt-click, only a part of it is selected. As you can see, this is what happens when trying to select the problematic loops. This red flag is a sign that the edge flow is being disrupted, and if we look at where our selection abruptly ends, we can see on both loops that the selection ends at the corner vertices, which unlike the rest of the loop vertices, are only connected to 3 edges rather than 4. If you examine the other vertices in the loop, you will find that they all are connected to 4 edges, and the angles between the edges are close to 90 degrees. However, the problematic vertices are only connected to 3 edges, with the angles varying from around 90 degrees to close to 180 degrees. These 3-edged vertices are known as end-poles. You may also encounter similar issues with 5-edged vertices known as E-poles, and any poles with more than 5 connecting edges are called high-degree poles. It is important to realize that poles will inevitably appear on the majority of 3D models. Rather than trying to remove or fix them, we as 3D artists must learn to strategically position and place poles away from important areas, usually on flat surfaces or areas that will not need to deform too much when animated. So, how can we divert the poles in this model in order to fix its edge flow? For these faces, and flat faces in general, the common practice is to inset the face and leave the inner region either grid-filled or empty of vertices. For the purpose of the example, let's say we are trying to have as little faces as possible, so let's inset the central circular grid fill and clear the faces with Ctrl-X in face select mode. Do the same for the bottom area. And now, if we try to select these loops, the selection manages to circumnavigate the mesh, indicating that we have fixed the edge flow, as there are no more end poles disrupting the loops. We'll look at more examples of directing edge flow throughout the series, but first, let's assess what we have just done, and how the techniques of edge loops, edge flow and poles are all connected. You may have noticed, but by insetting areas to avoid poles, we are actually just adding another loop that moves parallel to the original loop, moving away geometry that disrupts edge flow. As we learned before, having identical loops will ensure the subdivided result has perfect shading, as well as keeping its shape and sharpness intact. So to summarize, good edge flow is essential for having models that subdivide well, and good edge flow is disrupted by poles, and to fix our edge flow we move poles to less problematic areas, by adding edge loops that act as buffers, or supports, between the problematic geometry and our edges. That was a lot of information in a short amount of time. Let's walk through 1 or 2 more examples in this video before moving on to the next section. Remember, the best way to learn and improve is from practice. Following these examples is a good start, but the real improvement will come from you challenging yourself with independent projects, even if they are small or random. For the next example, spawn in a cylinder, giving it 16 vertices. In edit mode, scale it down on the Z-axis, and add a loop cut around it. Let's cut a hole in these for faces. Since this is a curved surface, we will use a boolean. In setting the faces and counting the surrounding edges shows us that our cutter will need to have 8 vertices, so spawn in another cylinder, this time with 8 vertices, position it, make the cut, apply the boolean and delete the cutter. Go into edit mode and clean up the boolean, sliding vertices and joining edges. Don.t forget to merge by distance afterwards. Now that we have our cut, go back into object mode and subdivide the model. By now, you should have recognized that each of these circular loops needs to have close neighboring circular loops in order for the Catmull-Clark subdivision algorithm to shade the model well and retain the original shape, which currently isn't the case for any of these loops. So select each circular loop and bevel it, using 2 segments and a shape of 1. Remember how before our bevel, the top and bottom loops were being disrupted by the diagonal inset edges of our cut. Although they weren't poles, the angles between the edges was closer to 45 than 90, confusing our edge flow. Notice how both in this example, where the angle was too small, and the older one, where the angle was too large, edge flow was disrupted. This is exactly why it is important to add these supporting loops. Instead of the diagonal edges being connected to the top and bottom loops, they are now E-poles and are connected to the supporting edges, where they are less problematic and subdivide well. If we look at the subdivided wireframe view, you can see the original top edge is perfectly circular, as the loops neighboring it were also circular. However, the subdivision algorithm has morphed the supporting edge, as it was not neighbored by 2 parallel loops, rather it was neighbored by a circular loop and the cut area, which has redirected the flow. Take a look at what would have happened if we hadn't added a supporting loop between the cut area and the top loop. In this case, the top loop has morphed to smooth out with the neighboring geometry and is no longer circular. This was an intense tutorial with a lot of new terminology and techniques. Don't worry if some of it was confusing, these ideas will be reinforced in the next video and throughout the series. For those of you who feel confident with this video, I challenge you to make this shape. I will share the method at the start of the next video. See you there. Remember to like and subscribe for more, and comment any thoughts or questions.